Okay, in this chapter we're going to be looking at energy. Energy can actually be broken down into two main categories in the chemistry field, and that's just potential energy and kinetic energy. Potential energy, and we're going to relate this to a physical thing. So we have kinetic energy, which is more like a waterfall, where the water is actually dropping off the edge of the cliff, going down, and releasing a huge amount of energy by falling. Potential energy would be taking that same idea, but putting up a hydroelectric dam, or just a dam in general, or a retaining wall, something that holds that water back. That potential energy comes from the fact that that water being held back could be funneled to go down like another waterfall and give us that kinetic energy. So potential energy is stored energy. Kinetic energy is energy from motion. And what links them two together is this law of the conservation of energy, which basically means that energy can be converted from one form to another, but it cannot be created or destroyed. All right. In the chemistry world, we're going to actually always measure energy as just from two things, heat and work. Matter of fact, we have this for an equation where we get those. So work is just a letter W, but heat, we use a Q. And heat and work are the only things that create our energy changes. And they are just what you think they are. Work is doing work, maybe moving something. Heat is heating it up. Now, a state function is a very particular type of calculation. It's a property of a system that's independent on its pathway. A good example to explain what a state function is, talking about the distance between like Chicago and Denver. The distance that you might travel to go from those 2 points would vary based on the path you take, because it'd be very difficult to walk in a perfectly straight line, but if you took the roads, depending on which road you take or which lane you're in the road, you might actually travel a slightly different distance. But what would be fixed is the elevation change between Chicago and Denver. Now, it might not be the elevation change you go through, but the overall sum of all those changes, the positives and negatives when they add up, would be the same, because Denver's at a very fixed elevation, Chicago's at a very fixed elevation, and the distance between those would then be fixed. So the change in the elevation is what we would consider a state function. That is independent of how we get there. The distance is not a state function because it really depends on how you get there. All right, let's relate this to some of a chemistry world. So in the chemistry world, we are dealing with system and surroundings. That's everywhere, but specifically in chemistry world, we are going to distinguish our energy change of the energy of the system and the energy of the surroundings. Now, for the most part, the energy that we see in a chemical reaction can be expressed very quickly by the heat coming off. Now, so we're going to focus mostly on the energy leaving, which is what this is talking about. This is talking about things like this. So if we take some methane and burn it in oxygen, it makes some CO2 and it makes some water. And we got to balance this. But that combustion reaction releases a bunch of heat. Heat is a product. That is something we call an exothermic reaction. It loses that energy, and it loses it as heat energy. Endothermic is one that absorbs the heat. We do see those. Instant cold packs are endothermic reactions, but it is all based on heat. But the heat releasing reactions are a heck of a lot easier to study because we can actually see them. It's hard to see when a chemical reaction does work, but it's quite easy to actually experimentally see the heat being produced. All right, so that thermodynamics, which is the study of that energy, is a very big area of chemistry. If you go into the chemistry field, this becomes a chapter, or this goes from a chapter in a textbook to an entire class. And even in that class, they don't ever touch on every aspect of thermodynamics. Now, ironically, it is just the energy, and this equation is the base equation. It's just how it expands in that big class. And it does expand on this these laws of thermodynamics. I mean, it's saying the first here. That obviously implies there's more than one. We're only focusing on the first because it basically just says the energy of the universe is constant. That gets back to that law of conservation of energy. It can't be created or destroyed. We're just moving it around. All right, so in our equation with that delta E equals Q and W, the sign of the Q and the sign of the W are very important to what's going on. Basically, you can view it as this. If the system gains energy, then its value is positive. So endothermic reactions put heat back into the system, therefore it's a positive. If work is done on the system, that's like piling up the work, so the work is getting positive. So the signs are based on how that energy goes in, but there is a sign convection. All right, now those of you taking physics, you will see that these two are opposite signs in physics. That is simply because we look at it slightly different between the two subjects. All right, when we measure our energy, this is the energy, this is the Q for heat, this is the W for work. These are the acceptable units. The first two are the main ones we see. Joule is actually the standard for SI. We actually do use calories just because you're familiar with them a little bit more. Food calories. Now, this is not the same as a food calorie. A food calorie, calories in food, should have a capital C always, and that's actually 1,000 kilocalories, or 1,000 calories, or 1 kilocalorie. It was just done in here in America to keep things simple, and kcals were, I don't know, a bit too confusing. All right, and if you ever need to convert from joules to calories, this is the equation. That's the conversion factor, and it is something I provide to you on your periodic table at the test time. All right, so heating. If we're going to actually apply this, we actually can see that everything that warms up or cools down in the chemistry world, doesn't matter where the source of the energy comes from, can be related with this equation right here. So the S there is what we call the specific heat. Specific heat's like a constant for a substance that tells you how much it warms up related to how much heat's put into it. That varies by the substance. That's why water heats up very, very slow compared to the pot that it would go into if you were boiling it on your stove. Now, along with that, the mass is important. That should make sense because it should obviously take more heat to warm up more water. So the mass is important. And then the change of temperature, or how much it changes, is important. All right, when we see this, our units for our specific heat are almost always joules per gram Celsius or joules per gram Kelvin. And ever so slightly, so often, you see instead of joules, you see the calories. So it'd be calories per gram degree Celsius or calories per gram Kelvin. Now, ironically, if I was looking at water, which is what this one is, this 4.184, that conversion, these numbers, this would be 4.184 because the Kelvin doesn't actually change here. We'll see why in a second. But this is actually just 1 in terms of calories for water. All right, now the reason the Kelvin and the Celsius don't matter is because we're looking at a change of temperature. I want you to think about this. If I turned this into Kelvin, I would just add 273.15 to it, and I would add 273.15 to that. Well, math calls that, what is that, an additive property? Since I'm adding, and then I'd be subtracting, they don't really do anything. So the nice thing is about our temperature, it doesn't matter if I give it to you in Celsius or Kelvin, you do just get the subtraction. And then you just do this math just like it's given there. So 4.184 times 7.4 times whatever 46 minus 29 is. All right, to get these numbers, that delta T and that mass in a nice little convenient location, we're going to use something called a calorimeter. Now, the reason this is important is because when you actually cause a chemical reaction to produce heat, it'd be almost the same as like a cup of hot water. If you put like hot coffee into a cup, that heat transfers into the cup and into your hands if you're holding it. That heat is going out into its surroundings. In calorimetry, we want to minimize that. We want to actually know exactly what the I don't know why I'm doing delta. We actually want to know exactly what the system is and totally what the surroundings are. So the surroundings, while it is the universe, we want to minimize it going out into everywhere. Now, a great way to do that is actually this thing on the left. That's actually just styrofoam cups. Now, if you ever put hot coffee in styrofoam, you know the heat doesn't transfer into those cups too well. So if we double wall, so put 2 styrofoam cups within themselves, we're going to insulate that really, really, really well. And at least for a time being, we've limited the surroundings. Now, it's not perfect. If you put hot coffee into styrofoam, it's not going to stay hot forever. It just stays hot longer, and the cup itself doesn't get hot. All right, if we're doing this in a professional setting, we're going to use a much nicer calorimeter. Now, the only thing that's really terribly different in these is the insulation is far superior than just styrofoam. A lot of the times it's got a vacuum in it, and all the air's been sucked out, because it turns out that lack of air totally isolates the environment and doesn't heat up at all. And then, you notice how this says electrodes? We can actually put something in here that will burn if you run electrical current to it. They sometimes call these bomb calorimeters, not that they're going to blow anything up, but if you put a very small amount of a explosive material in there, you can get the energy out of it. Because not trying to blow up this thing per se, just trying to get a lot of heat out of it. Ironically, when we do this in our chem labs, we actually do use the styrofoam, and we get really, really, really good results. So spending the money on that is unnecessary for how we use it. All right, when we actually see that heat is coming from a chemical reaction, we actually can relate that to this cool thing called enthalpy. Now, what I mean by that, turns out when we burn CH4, so that equation I had up there a couple slides ago, we said before, or I said before, that produces a lot of heat. Well, more specifically, it produces 890 kilojoules per mole of CH4. So if I wanted to know how much energy is burned from 5.8 grams of methane, I actually am just going to do a nice little conversion factor. I'm going to figure out how much a mole of CH4 weighs, and I'm going to do that from the periodic table. So fire up my calculator here. A carbon weighs 12.01, and I'm going to add 4 hydrogens to that. Oops, I missed a 0. And I get a molecular weight for methane, CH4, of 1604. Now, once you have moles, now we're going to use this as a conversion factor. So 890 kilojoules per mole. So that reaction, that 5.8, would produce, let's see, 5.8 divided by that value there times 890, that would produce 322 kilojoules. All right, now to put that in perspective of food, I'm going to divide this by that 4.184. So that is going to burn and release that many calories. So that's 0.07 food calories. So 5.8 grams produces a significantly less amount of heat than even a Tic Tac does. Okay, next thing we're going to look at is how to use those delta H's I just gave and actually create a delta H for a reaction that's not been studied. So what I mean by that, we need to be able to take any reaction, so reactants going to products, and get a delta H for it. Well, Hess's law, Hess was a guy that figured out how we could do that. So what he is able to find is if we had a bunch of other somewhat related equations, we can use those to build the equation we want. All right, what do I mean by that? All right, so I want you to look at that overall process up there. And I already put the delta H up there. But let's say we didn't have this yet. So I'm just going to put a line through it, and we don't have it. But let's say we knew these two down here, and we did have delta H's for these. All right, you notice how they're similar, but not quite the same? Both of them have this NO in them, but it's not in that overall process. So it looks like having these delta H's isn't really accurate because they're not really that same equation. Well, Hess was able to show that if we can somehow combine those two equations in such a way that they look like the original, then we can combine the delta H's as well. And what I want you to notice is, think about this. Let's say we added these two equations up. So I'd have 1 and 2. I'd have two O2s. Now this NO, see how there's 2 of them? There's also 2 of them over here. They kind of cancel out because the products and reactants work that way. And NO2. So you notice how this new equation is that exact same equation up there? Since we can add these two equations to get that, we actually can add these two delta H's. I'm going to just put a 1 here and a 2 here for equation 1 and 2. But we can just add them up. Alright, let's give that a try for real and see what we get on this, because we're actually going to be able to get some pretty interesting calculations here. Alright, so this is the equation we're going to look at. Up at the top I gave you an overall process. I'll just put an O there. And then I gave you equations 1 and 2. We're going to try to recreate that overall process using equation 1 and 2. Alright, what we're going to do to make this work is just realize where our components are. Now, I'm not going to focus on the oxygen yet because it's actually found in both equations. But you see how the SO2 is only right there and the SO3 is only right there? We're going to build the equation from just looking at those guys. Alright, so my overall process has SO2 as a reactant. Equation 1 has it as a product. So the very first thing I'm going to do is I'm going to rewrite equation 1, but I'm going to reverse it. Alright, now I want to actually do something about that SO3. But you see how this has 2 SO3s in the equation, but up there was only 1? I'm going to take equation 2. I'm going to multiply all the coefficients by 1/2. So that is actually just 1 SO3. So I would have just a single sulfur. This is going to be weird. I'm not going to have 3 oxygens. I'm going to have 3 halves of an oxygen. 3 times 1/2 is 3 halves. And I am allowed to have fractions now. And just an SO3. Alright, the neat thing about this now, we've just applied our 2 equations, but if you notice I have sulfur on both sides. It would cancel out. And that 1 oxygen would cancel out one of these and leave us with just 1/2 of an oxygen. So we'd have an SO2 plus 1/2 of O2 giving us SO3. Which turns out that's our overall process. Alright, so we've manipulated our 2 equations, equation 1 and 2, and we're able to generate that overall process. That doesn't mean we can add those H's yet because we did some manipulation. So you notice how we reversed equation 1? Since we reversed it, we're going to reverse the delta H for equation 1. So instead of being negative 297, it's now positive 297. That's all it takes to reverse it. Just put the energy back into it. Alright, equation 2, I took half of it. So I'm going to take this negative 792 kilojoules and I'm going to multiply it by 1/2. And then those are the values I'm going to add up. So negative 792, I didn't put my negative in. Negative 792 times 1/2 added to positive 297. That overall process should be negative 99 kilojoules. Alright, our method is always the same. We're going to kind of work with our equations, going to build our products and reactants from the overall processes, going to have to reverse equations to need to, going to multiply to get the coefficients right, and remember you're allowed to have fractions now, so don't worry about that. Let's give another try with a slightly more complex one. Alright, reason I say more complex, I have a lot more elements. But we're going to do the same type of thing. Now, what I mean by that, if you notice, I have NH3, that's the only time it's used up here, and that's the only time it's used here. So I'm going to just call this equation 1, call this equation 2, and this is the overall. And the very first thing I'm going to do is take equation 1. I need to multiply all the coefficients by 4 to get that 4. And I need to reverse it. So I'm going to have 4 halves into, or 2 into, 4 times 3 halves would be 6. And 4 NH3 gases. Alright, the next thing I'm looking at, I'm not going to focus on this H2 because it's found in 2 locations. I'm going to focus on the O2. You see it right there? Alright, so I'm going to take equation 2, going to multiply everything by 3 in it, so I get that 3, and I'm also going to reverse it. So this is 6 H2Os, go to 6 H2s, and 3 O2s. And our 6 H2s would cancel out on both sides, so overall I'd have 2 N2s and 6 H2Os, giving me 4 NH3s and 3 O2s, which is our overall process. So, we're going to manipulate our H's now. This one, equation 1, we're going to multiply by 4 and reverse the sign. And the second one, we're going to reverse the sign and multiply it by 3. So, 4 times 484 minus 46 times 3. And we get 1798 kilojoules. All right. Oh, yeah. Next thing we're looking at, I hit end rather than next. Next thing we're looking at is we're going to actually focus on a bit on the work itself. Turns out work actually is an interesting loss of energy. Now it's weird to say it degrades its usefulness. Really what that's getting to, work is not as an efficient of transfer of energy as heat is. To say it's not useful is somewhat misleading, because if you think about it, a car, for instance, does get us from point A to point B because the pressure released in that chemical reaction pushes the pistons up and down. It creates work. And if that reaction didn't create work, your engine wouldn't work very well. It'd get hot well, but that doesn't get you from point A to point B. So to say it's not useful is a weird way of saying it. It's not so much that, it's just not as efficient. Alright, the reason this is, when we actually do a chemical reaction like that combustion, the energy of the heat and the work go everywhere. It's actually spreading all over the universe. And as it does so, it actually does so quite evenly. So our internal combustion engine, your car engine, is actually directing that into a very specific flow. It does it relatively efficiently for what it's capable of, but there's still room for improvement. Alright, so let's actually get some terminology here to help us understand what we're talking about on this complexity and why it's not efficient. So I have this nice little example here. I have this picture of these 2 glass flasks that are connected between the 2 with this little valve. On one side I have a gas. It's an inert gas like helium or neon. On the other side I have a pure vacuum. Alright, what's going to happen if I open that valve? Well, that's simple. It's going to distribute evenly between the 2 sides. Now, is there anything I can do to that valve to make that go backwards? No. Alright, that spontaneous change is what we're seeing as the driving force of the universe, or one of the driving forces of the universe. The Particles want to get spread out as much as much as far apart from each other as possible. The same as the energy, heat, and work. It just goes to spread out. And it's not spontaneous to go backwards. It will actually take a little bit of effort to put all the gas molecules on one side as opposed to the other. Can't do that quite yet. All right, so our driving forces for all of our chemical reaction is the energy wants to go everywhere and the matter wants to go everywhere, spread out. We kind of see that in that combustion experience example, for instance. If we were to burn methane and just let it burn, the heat goes in every direction. It spreads out to the universe whole as far as it can. Obviously, it gets the stuff near it first, but it will eventually spread. The matter does the same thing. The carbon dioxide and the water vapor that's being produced in that chemical change will go everywhere as well. It's not like they stay around there. Both of those will spread out. Chemistry world, science world, physics world talk about that spread or that increasing of chaos as entropy. So entropy is just a driving force to create more and more disorder. Everything's wanting to get as far away from each other as possible, and in a most disorganized state it can possibly get, or the most random state it can possibly get. Alright, now interesting, we're not going to do much more other than introduce the concept of entropy at this time. In later chemistry we'll go into more detail with it and explain how it's affected by various different things, but it is just a measure of chaos. So even in this picture of solid and gas, it should make sense that a gas water molecule would have more randomness or more chaos because it can move around. While solid ice, the ice molecules, the water molecules can't move around, so it has less entropy. And we're going to look at that in a lot more detail in later chemistry classes, but right now we're just introducing it as a term. Alright, that actually finishes it up with this chapter because entropy is just actually going to be where we end. We're not going to do any calculations with it. We're just actually defining it. All right. Have a good day.